Hey everybody, welcome back to the channel Stats with Aaheli, and this is Aaheli Bhattacharya, your statistics buddy. But today we are going to study linear algebra, right? Okay, so we are going to cover some of the most important and beautiful ideas of linear algebra today. As you can see on the screen, that is basis, coordinates, and the replacement theorem. And later on this video, we will study what are the real life application of replacement theorem and deletion theorem. All right, deletion theorem we have already studied. Now, in these slides which I have made, I want to show you something. That is, if you click on this part, this watch on stats with Aaheli, that means that this will redirect you to my YouTube channel. Okay, and if you are new here and not subscribed to me yet, then you can click here, and then this will go to the confirmation of subscription. Okay, so I hope that you subscribe, and let's move on with the slides. And a little more thing which I need to show you is that if you click on these contents, then you will see that this will redirect you to the part of the section in this slide. Okay, for example, if I show you that I want to study replacement theorem at first, see, this is the slide is going directly to the replacement theorem portion. I'm sorry. Yes. So this is going directly to the replacement theorem portion, right? So this is how you manage the slides which I have made, and I have made it with a lot of hard work. So I hope that you appreciate it. Okay, coming to the first part, like from the starting. Okay, so first is this theorem. Okay, this is the big theorem, and this is something very important for us, that is basis theorem. Now, in our previous videos, we were learning about basis, right, and how to prove a basis. We have proved a basis on two conditions. First is that if S is a set of vectors, then we need to prove that S is linearly independent in V, and next is that S generates V, right? But in this theorem, we will learn that if this proves to be a certain condition, then we can say that only linearly independent. If we prove that, then we will say that it is a basis. Now, just put your eyes on the theorem and let us study this theorem a little more. Now, see, this is the foundational theorem that ties everything today. Okay, so yes, what is the theorem saying? It is saying that if V is a vector space of dimension n over a field F, then any linearly independent set containing exactly n vectors is a basis of V. Now, what is this in simple words? What am I trying to say here? I'm trying to say that if your vector space has dimension n, you do not need to check the spanning separately. All right, just show that your n vectors are linearly independent, and that is like morely it. Okay, and they form a basis. And that is the power of this theorem. Now, if I come to the questions of it, then you can understand what am I trying to show here. See, in this question, we need to show that this set is a basis of R3. And what is the set here? This is given here. And we will show that first we will take the three scalars taken from the field, and then we will show that which are the vectors we are taking. This is alpha 1, this is alpha 2, and this is alpha 3, right? And then we will show that what is the dimension of R3. It is 3 only. And here we can see that by the basis theorem, it suffices to show that S is linearly independent. But for linear independence, we must show what is the rule of it. It is C1 alpha 1 plus C2 alpha 2 plus C3 alpha 3 is equals to 0, or theta, which is null vector. Okay. Now, what do you do here? You will substitute the values of alpha 2, alpha 1, alpha 2, and alpha 3, right? Here, and then you will show that C1, C2, C3 is equals to 0. Okay. Now, if you do it, then what is the next step? Next step is that you will multiply the scalars. You will just multiply it, and then you will do what? You will add the vectors, right? Do the component wise vector addition. Now, if you see C1 plus C2 plus C3, and then C1 plus C2 plus 0, then C1, and then 0 plus 0, it is 0 only. Now, from this system of linear equations, we got three equations, right? That is, this first equation is equals to 0, second equation equals to 0, and third equation equals to 0, right? From here you can see that. And next is that from C1, from the third equation, we can directly see that C1 is equals to 0. Now, if we put C1 is equals to 0 in this second equation, then we will get what? C2 is equals to 0. Now, since we have got that C1 and C2 both are 0, then we will put that value in the equation 1, and we can see that C1, C2 is equals to 0. Then C3 is also equals to 0, right? So from here we have shown that C1 is equals to C2 is equals to C3 is equals to 0. Therefore, S is linearly independent. Okay, so this is by the theorem which we have proved. and that S is a basis of R3. Now you have to see something which this is the just a question. I have not shown like handwrittenly because I have written all the steps here. I will show the few questions in the later portion of this video only. That is on these first two questions we can do very nicely and easily with the substitution method, so I'm not showing that to you in like written form. So anyway, I will come to the Cramer's rule part in the last two questions where the equations are a bit difficult to follow along with the substitution method. So that time I will show it in my journal. All right. Now see, in this in basically in this question we have shown that that the set of vectors is linearly independent, and then we showed that the linearly independent vectors in a three-dimensional space. That is important by our theorem. Then we could say that this is a basis of R3, and hence it is proved, right? Now coming to the next question, this is also very important. Okay, here we will show that verify that the set S, here these two other vectors, is not a basis of R3. Now here you can see that this looks like a very contrast of the question, right? Now here is a simple answer. It is no, right? And why am I saying no? Because you can see that R3 has a dimension of 3, but we only have two vectors here. The number of elements in the set must equal to the dimension of the vector space. Since 2 is not equals to 3, we already can understand that. Then we can say that this set cannot be a basis of R3. This is as simple as that, right? This is just that. See here, I have written only that. Now coming to the most important thing which of today's class, okay, that is the replacement theorem. Now this is where things get really, really interesting. Now we will talk about replacement theorem. First, you need to understand the statement. If you read the statement aloud, then you can only understand it yourself that what does it mean. See, I am explaining you the statement. The statement goes like, suppose that you have few a set of vectors like alpha 1, alpha 2, alpha 3 goes on till alpha n, which is a basis of vector space V. Now if you say that if beta is any non-zero vector in V, it can be written as a linear combination. Beta is equals to C1 alpha 1 plus C2 alpha 2 and goes on till Cn alpha n. Now I'm saying what? This is an important condition for this theorem. This is that if some coefficient Cj, suppose there are C1, C2, C3 and goes on till Cn, right? And I'm just supposing that there is a coefficient Cj which is not equals to 0. Then I am saying that we can replace that aj for which is the for coefficient of what, of our vector, right? Let us say that cj is the coefficient of vector aj. So we're just saying that if we can replace that aj with beta, and the resulting set is still a basis of v. Now, this is what the theorem says in that statement, right? Now, in plain English, what am I trying to say? I'm trying to say is that if a vector beta can be expressed using the basis and it has non-zero contribution from basis vector of aj, then beta can step in and take aj's place, okay, without breaking the basis. Now you can see I have put an example here. See, I have given the intuition behind of what to understand from this theorem. Okay, before understanding the theorem, you can read the intuition and see in this example, what am I showing here? In this example, I am saying that we take our basis to be 1, 1, 1. Like there are three vectors, and we were saying that let beta be 2, 2, comma 1. Okay, can we write it using the basis? Just see that 2 comma 2 comma 1 can be written as 1 into 1 comma 1 comma 1 plus 1 into 1 comma 1 comma 0 plus 0 into 1 comma 0 comma 1. And if you just follow along the steps, if you want to verify it yourself, you can do it on your home, and you will see that yes, we can write that. We can write 2 to 1 as a combination of the other vectors which were given us in the question, right? And the coefficient of, let us say that the coefficient of the first vector, which is 1, 1, 1, is 1, right? Which is non-zero. So we can replace 1, 1, 1 with that the new vector that is 2, 2, 1 that we were choosing as beta, right? So then our new basis will be what? 2 comma 2 comma 1. This is the first vector. Second vector 1 comma 1 comma 0. Third vector is 1 comma 0 comma 1. That is still a valid basis in R3. All right. Now coming to the next question. Now see, what is this showing? This question is saying that find the coordinates of the vector 131 relative to the ordered basis B. Now here this is given, our set of vectors is given. Okay, now we will need what? We will need the C1, C2, C3 or the scalars which were taken from the field, right? Such that 131, this is given to us, is equals to C1 into this first vector which is alpha 1 plus C2 alpha 2 plus C3 alpha 3. And then we will get three equations from here. So we got this equation C1 plus C2 plus C3 is equals to 1, C1 plus C2 is equals to 3, and C1 is equals to 1. So from here we can say that this is directly, we can see that from the third equation we are getting the C1 is equals to 1, and if we put the third equation's value in the second equation, then we can see that 1 plus C2 is equals to 3, therefore C2 is equals to 2. And if we put the values of C1 and C2 in equation 1, we can see that 1 plus 2 plus C3 is equals to 1. Therefore, C3 is equals to minus 2. Therefore, what is our answer? How do we get the answer? Answer is that the coordinates of 131 relative to B is equals to 1, 2 and minus 2, as you can see here, right? So this is all about the question which I've told you that there are two questions on substitution method only. I will solve and I will show you, and here that is it. Now, if you want to quick check of intuition, notice that these coordinates are not as the same as the vector's components. Why? That's because we are not in the standard basis anymore. We are on our basis. This is not the standard basis as 1 comma 1 comma 1 like that, 1 comma 1 comma 0. So, oh, anyway, coming to the next question. Okay, in this question, you can see that here again we are saying that find the vector in R3 whose coordinate vector related to the ordered basis B is this. Okay, so again, this is a similar type of question which I have already shown, right? So here, what you need to do, this is a kind of intuitive question, right? So this is basically how will you do it? Just a moment. Now here we can see in this question that this is basically the reverse of the previous question we just solved, right? Now we have been given that the coordinate of some vector relative to the basis, we are given the vectors, is 152. Now what is the actual vector? Now this one is basically very straightforward, as I was saying that this is very intuitive question. Just plug in directly. That is 1, that is we are given the this vector, right? 152. Okay, where is it? Here, 152. Now you will put what is this 1? This is the C1. So it will be 1 into 1 comma 1 comma 1, then 5 into 1 comma 1 comma 0, then 2 into 1 comma 0 comma 1. Then what are you getting? We are getting to be 8, 6 and 1. Then the vector is basically 8, 6 and 1. Okay, the coordinates gives you basically the recipe, and the vector is what you bake with it. That is something very simple which I have to tell you. Okay, now coming to the next question. Now here I will start with the values. We will find the values with the Cramer's rule. Okay, now this question I will show it in my journal, so just a moment that I change my slide. Okay, so now we are doing this, the second problem, the third actually of today's class. So we are going to do it using the Cramer's rule, right? So let me write down the question here first. The question is that find the coordinates for the vector 2, 3, 1 relative to the ordered basis. Now what is the ordered basis which we have got? It is 1, 2, 1, 2, 1, 1 and 1, 1, 2. Okay, it is 1, 2, 1, 2, 1, 1 and then 1, 1, 2. Okay, so from here how will we do it? See, we need to do the first setup. Setup is what? That is 231 is equals to C1 alpha 1 plus C2 alpha 2 plus C3 alpha 3, right? So what is our alpha 1 and alpha 2 and alpha 3? It is just this alpha 1, alpha 2 and alpha 3, right? So let us set up the question. How will we write it? Solution is that 231 is equals to C1 121 plus C2 211 plus C3 1 comma 1 comma 2. Now we will get from here the three equations. What are the three equations? That is 1 into C1 plus 2 into C2 plus 1 into C3, that is our first equation. So let me write the equations in red color. C1 plus 2C2 plus C3 is equals to 2. And then 2C1 plus C2 plus C3 is equals to 3. And then is equals to 3, and then comes C1 plus C2 plus 2C3 is equals to 1. So this is my first equation, this is my second equation, and this is my third equation. Now from here, how will we try to do it using Cramer's rule? We first need to find the coefficient matrix, right? And we will find the determinant of it. So what is our coefficient matrix? Let us take this color. A is 1 2 1, 1 2 1, 2 1 1, 2 1 1, and then 1 1 2. 1 1 2. This is our coefficient matrix, and now we'll find the determinant of it. And we already know how to find determinants, right? So it is 1 into 2 minus 1 minus 2 into 4 minus 1 plus 1 into 2 minus 1. And let us further calculate it. That is 1 into 1, 1 into 1 minus 2 into 3 plus 1 into 1, which is equals to 1 minus 6 plus 1, which is equals to minus 4. And we have got our coefficient matrix, and now we will do what? We will take A1. Now what is A1? A1 will be, first we will be replacing the first column with the constant matrix, right? What is our constant matrix? It will be 2 3 and 1, right? So let us do that. A1 will be the first column will be 2 3 1. That is our constant matrix, and the second and third column will be same as the A matrix, right? So 2 1 1, and then 1 1 2. And next you need to do what? You need to find the determinant of A1 2. Now let us find the determinant of A1. It will be 2 into 2 minus 1 minus 2 into 6 minus 1 plus 1 into 3 minus 1. Okay, now if we further calculate it, we will get what? 2 into 1 minus 2 into 5 plus 1 into 2, which is equals to 2 minus 10 plus 1, which is equals to minus 6. Now, how will you find what is our C1? C1 will be what? Determinant of A1 by determinant of A. So, let us write it. Therefore, C1 is equals to determinant of A1 by determinant of A. What is our determinant of A1? It is minus 6 by determinant of A is minus 4. So let us write that minus 4. So if we calculate it, we will get what? 3 by 2. So that is our C1. Okay, so we have got our first value. The next unknown value is that C2. So for that we will need A2 matrix. And what is A2 matrix? We will replace the second column with the constant matrix, and the other two columns, that is the first and the third, will be remaining same as the A matrix, right? Original matrix, original coefficient matrix. So let me put A2. A2 is equals to what? Okay, what is the first column? It is 1 to 1, right? 1 2 1, and our constant matrix is what? 2 3 1. So second column will be 2 3 1, and the third column is the 1 1 2. 1 1 2. And next we need to find the determinant of A2 2. So how will we get it? 1 into 6 minus 1 minus 2 into 4 minus 1 plus 1 into 2 minus 3 will be equals to 1 into 5 minus 2 into 3 plus 1 into minus 1. So how are we getting it? 5 minus 6 minus 1. So it is basically minus 2. So from here we got the determinant of A2 to be minus 2. And then we will do what? How will we find C2? C2 will be what? Determinant of A2 by determinant of A. So let us write it. C2 is equals to determinant of A2 divided by determinant of A. And what is determinant of A2? It is minus 2, and determinant of A is what? Minus 4. So minus 2 by minus 4 is basically 1 by 2. And that is our answer. Okay, so we are finding the coordinates, right? So we have found our first coordinate, second coordinate, and now we want to find the third one. How do we find the third one? We will need another matrix A3, right? And for A3, what do we need to do? We need to replace the third column with the constant matrix, and the other two, which is the first and second column, will be remaining same as the original coefficient matrix. Now coming to what is A3. A3 will be what? 1 2 1 and 2 1 1, the same as the first two columns. Third column will be what? Third column is the the constant matrix. So that will be our constant matrix set, which is the 2, 3, and 1. Now we will find what is the determinant of it. So how will you find it? 1 into 1 minus 3, and then 2 in minus 2 into 2 minus 3, and then plus 2 into 2 minus 1. So 1 minus 2 minus 2 minus 1 plus 2 into 1. And if we further calculate it, we will get what? Minus 2 plus 2 plus 2. So it is basically 2, right? So we have got our determinant of A3. Now we will know the third coordinate, right? Which is a C3. C3 will be what? Determinant of A3 by determinant of A. All right. So let us write it. C3 is equals to determinant of A3 by determinant of A, which is equals to 2 into 2 by minus 4, which is minus 1 by 2. So this is our third coordinate. So basically from here, what is the result we got? The result is that our first coordinate was what? 3 by 2, right? And the second coordinate is half, and the third coordinate is minus 1 by 2. So just write it like this, that therefore 3 by 2, 1 by 2, and minus 1 by 2 is the coordinate. And that is the answer for this question. Okay, fairly simple. Now we will come to our second question. Now, second question is again similar to this one, but here in the second question, again we will solve using the Cramer's rule only, not with the substitution method. So, just a moment. Yes, so for in this question also we will be doing that the same type of problem, which is we need to find the coordinates, right? And here also we will do by the Cramer's rule. So, coming to the question is find the coordinates. These questions are also written in the slide, so when you are watching the notes and you want to refer how will you solve this kind of questions, you can click on that link of my stats with Aaheli wherever it is written, and then you can see from this video. Okay, so yes, find the coordinates for the vector 331 relative to the ordered basis. What is it? S is equals to 1 comma 3 comma 1, 3 comma 1 comma 1, and then 1 comma 1 comma 3. Okay, so this is our question, and for this question to solve, again we will do what? We will set up the first rule, that is 331. Here 331 will be equals to C1 alpha 1 plus C2 alpha 2 plus C3 alpha 3, and we will find the C1, C2, and C3, and those are the coordinate of which is asking in the question, right? So let us do that. So solution will be 331 will be equals to C1 1 comma 3 comma 1 plus C2 3 comma 1 comma 1 plus C3 1 comma 1 comma 3. And from here we are going to get three equations, right? So what are the three equations which we are getting? That is C1 plus 3C2 plus C3 is equals to 3. Then 3C1 plus C2 plus C3 is equals to again 3, and then third equation is a C1 plus C2 plus 3C3 is equals to 1. Now what is the next step? Next step is to find the coefficient matrix, right? So let us find the coefficient matrix. A will be equals to 1 3 1 3 1 1 and then 1 1 3. All right, now we are going to find the determinant of this coefficient matrix. What is it? 1 into 3 minus 1 minus 3 into 9 minus 1 plus 1 into 3 minus 1, which is basically equals to 1 into 2 minus 3 into 8 plus 1 into 2, right? Which is equals to 2 minus 24 plus 2 is equals to minus 20. Okay, so I think you can see the okay, I don't know why is this coming here. Anyway, this is the A matrix, which is the coefficient matrix. Okay, so from here we are getting that our determinant's value is minus 20, and then we will try to find out what is the determinant of A1, A2, and A3. How will we find determinant of A1? We will substitute the value of the column matrix with the constant matrix. What is the constant matrix? It is 331, right? So for the A1 we will do that. Let us do it. Then we will come to the A2 part. Okay, so how will we do A1? A1 will be substituting the column matrix for the first part, okay, first column. So it will be 3 3 1, and then 3 1 1, and then 1 1 3, and then we need to find the determinant of it. So it will be 3 into 3 minus 1 minus 3 into 9 minus 1 plus 1 into 3 minus 1. Okay, so which is basically 3 into 2 minus 3 into 8 plus 1 into 2, which is equals to 6 minus 24 plus 2, which is equals to, I'm sorry, this is yes, plus 2, which is equals to minus 16. Okay, now how will we find c1? C1 will be what? Minus 16 by 20. Okay, so we can find it like here only, or we can find it later on. Let us first find what is the a2 a3. Okay, a2 and a3. So a2 will be what? Now we will replace the second column with the constant matrix, right? So it will be 1 1 3, no, 1 3 1, I guess. Yes, 1 3 1, 1 3 1. The second column will be 3 3 1, 3 3 1. Third column will remain the same, that is 1 1 3. Okay, so now we will find the determinant of this. So how will we find it? It is basically 1 into 3 minus 1, sorry, 9 minus 1, and then minus 3 into again 9 minus 1 plus 1 into 3 minus 3. So it is basically 1 into 8 minus 3 into 8. Okay, so 8 minus 24. So it is basically minus 16 again. Okay, so this is our a2. Now from here we are getting what? From here we will get our c2. Now next is a3. How will we find a3? A3 is that we will replace the third column with the constant matrix, and the other remaining columns will be remaining same. Okay, so what is it? 1 3 1, then 3. Okay, what is the second column? 3 1 1, 3 1 1, and the third column is that 3 3 1. Okay, so 3 3 1 will be equals to, now we will find the determinant of it. So how will we do it? 1 into 1 minus 3 into 3 minus 3 plus 3 into 3 minus 1. Okay, so it will be 1 into minus 2 minus 3 into 0. Okay, this is cancelled, plus 3 into 2. Okay, so we are getting what? Minus 2 plus 6, which is equals to 4. So this is our a3, right? So now we will do what? We will find our c1, c2 and c3. How do we do it? C1 is equals to determinant of a1 by determinant of a. So what is our determinant of a1? You can see that is minus 16. And what is our determinant of a? That is minus 20. Okay, so we will do what? Minus 16 by minus 20, and minus 16 by minus 20 is basically 4 by 5. 4 by 5. Then C2 is equals to what? Determinant of A2 by determinant of A. And what is determinant of A2? Let us see. That is again minus 16. Okay. And divided by minus 20. So minus 16 by minus 20 is again 4 by 5. And C3 is equals to what? Determinant of A3 by determinant of A. And what is determinant of A3? It is 4. So 4 divided by minus 20. And 4 divided by minus 20 is again minus 1 by 5. So 4 divided by minus 20 is again minus 1 by 5. So this is our coordinates. These are the coordinates C1, C2 and C3. So while writing the answer, you will write what? Okay. Answer is coordinates. Coordinates are what? 4 by 5, 4 by 5, minus 1 by 5. So this is our answer for this question. Okay, now we will move on. We have solved the typical kinds of questions which we usually get for this kind of topics. Okay, for replacement theorem we did, and we did for the basis one also, which is the modern method. Okay, which is the next step of basis, right? That is, only we are proving that it is linearly independent and the dimension of the r will be equals to the vectors, then it we can say that it is a basis. Now next is the interesting and the highlighted part of today's video, that is the real life application of today's video, today's theorems which we studied. That is, the first is replacement theorem, and previously we studied deletion theorem, right? So from that, this is important, and you can do a little bit of research on yourself, right? That is on the real life applications of any topic which you study on linear algebra, because that is very important and this will bring intuitions on your head a lot. Okay, now I'm changing the slide to my html file so that I can show you the real life applications. Okay, just a moment. Okay. I hope this is visible. And these were our questions. Now, here, as you can see, that here in this slide also, I have written everything properly. I have written the coefficient matrix, and then I have shown the determinant of A, and then I found what is A1, and then showed what is C1. Then, like this, similar wise, I have shown everything step by step in the slide also. Even if you don't understand from this, you can see from my video. Okay. So, that was all for the questions part. Now we are coming to real life applications. Okay, so these are the real life applications. First we will study, we will understand what is the real life application in linear algebra of replacement theorem. Okay, so the first point which you can see, that is the engineering and coordinate system. Now let me explain you. When engineers describe physical space, they use a lot of axes, right? The set of axes like x, y, and z. Now those axes form a basis. Now if you rotate those axes, which happens all the time in robotics and physics, okay, you're literally applying the replacement theorem. You are replacing the old basis vector with the new ones, right? When you're rotating it, it is becoming the new axis, right? So the space didn't change. What is it that is changing? Just your description of it did, right? This is used in robotics, computer graphics, and physical stimulations every single day. Okay, now coming to data science and machine learning. Data science is one of the subject which I am going to learn too. Okay, so yes, that is something interesting for me. Okay, in machine learning, your basis vectors are your features. This is very, very interesting. See, for example, like this is very intuitive also. You can understand from this example, this application a lot better. Things like height, weight, age, etc. These are the features. Okay, sometimes instead of using height and weight separately, you replace them with a single new feature called BMI. Now, what is BMI? Everybody knows what is BMI, right? That is body mass index, and which is basically a combination of both height and weight, right? And that is literally the replacement theorem. Okay, that is replacement theorem in action, you can say. We have replaced two original basis features, which is height and weight, with one combined feature that still captures the same information. Okay, this is what replacement theorem does in the real life. And next you can see the application number 3. Okay, so what is application number 3? It is project management and the deletion theorem. So the first two applications were on replacement theorem, and the last two applications are on deletion theorem. Okay, so here's a fun one. Okay, imagine a project team where person A collects a data. Suppose that I am collecting a data, and my friend, that is person B, is analyzing it. Now we have got another friend. Okay, suppose person C, and that person analyzes the data the same way as my friend does. Now here we can say that person C's work, that is our common friend's work, is basically redundant, right? Like we do not need that. Even if we remove that person, we won't change the output because I'm collecting the data and my friend is again analyzing it. So this is what the deletion theorem basically says, right? If a vector, which can be a person or a task, right, can be expressed as a combination of others, then removing it doesn't affect the span of the team's work. Okay, now this was a fun one, right? Anyway, coming to another intuitive game of deletion theorem. See, this is again very simple and you can understand from the example written here itself, right? That is, suppose that you have got three routes to get from home to mall. Okay, this is a, and in a very broad basis, deletion theorem is used in navigation and route optimization. Okay, like in GPS and in Apple Maps, like that. Okay, so suppose that you have got three routes. Route A is that home, then you go to the park, and then you go to the mall. And route B is that home, then to school, then to mall. And then route C is that home to park to school and then to mall. Now route C is basically just a combination of route A and route B, right? Now if I remove route C, then also I can reach the mall, right? Just like a linearly dependent vector, removing it doesn't reduce your reach. Okay, so basically that is all what we have learned in today's class, and let me show you the summary of all the results. Is that these are the questions which we did, and in this summary you're gonna get everything of the result of all the answers. And okay, so basically you can see from the summary. And now, okay, that is all for today's class, I guess, because here I can see the key takeaways. Okay, now let me wrap our today's class. Okay, first is what we learned is that any n linearly independent vectors in an n dimensional space forms a basis. Now, this is the one line which you need to remember all through linear algebra when you are studying about basis, and because basis is everywhere and you need to learn this line. Okay, this line is very very important, so I'm repeating it. That is, any n linearly independent vectors in an n dimensional space forms a basis. Okay, next, what we learned is that to prove linear independence, we have to set the linear combination equal to 0 and show that all constants must be 0. We already know for linear independence, right? Now coming to coordinates of a vector will be equals to the scalar of the scalar you need to for a specific basis to build that vector. Okay, which we did the questions on, right? And the next is we studied the replacement theorem, which says that we can swap the basis vectors with the new ones as long as those new vectors will have the non-zero contribution. Okay, non-zero, the coefficient is non-zero, right? The vector's coefficient is non-zero, that is what I'm saying. Okay, now this basis is like in everywhere. Okay, that is what we studied in the later part, which is the real life applications. It's like in robotics, it's in AI, it's in data science, it's in navigation, which we use in daily life. Even I can give you an example right now, that once I was see, I was doing it, that is, I forgot my password, and then there I wrote my previous password, and then I wrote my next current password, and then the new password, right? So I'm basically doing what, I'm replacing the old password with the new password. So that is where also the replacement theorem is in work, right? So when you're going to learn all these things in broad basis, like in machine learning or in data analysis or data science and AI and mathematics and computing, then you will see that these theorems which we are learning and doing questions on are on practical work, right? So yes, and that is basically, I think, all which we have seen reconstruction from coordinates. Okay, which we have did, and that is basically all for what of today's class, right? And if this video helped you, please hit the like button and subscribe if you're new. And drop your comments in the comment section. Drop your questions in the comment section, and if you have any, and if you have any kinds of doubts, any kinds of problem, or regarding the notes or anything, you can also share with me. And yes, I do read all the comments, so yes, see you there. And keep learning and keep doing mathematics until the next video. We will be doing more things on linear algebra. Okay, so yeah, bye bye, take care.